Alright, what's up Logic fans? It's Ash again, coming with section 3.9, our ninth and final section in chapter 3. We cover Advanced Indirect Proof techniques. So we're going to presuppose that you understand both CP and IP already as we launch into this video. So if you don't have those down, go check out the previous videos starting on 3.7. Alright, let's rock. Alright Logic fans, let's jump right in and begin discussing some advanced applications of indirect proof. So essentially what we're going to be discussing today is combining CP and IP in a single demonstration. Okay, and there's some various aspects of this that we'll discuss throughout, but the basic idea is you can nest multiple CP assumptions together, and in addition to that, have a final IP assumption if you like. Now, as usual, you don't have to use these techniques. The rules, whatever can be proven with CP or IP can be proven without CP and without IP. That's always true, but some problems are exceptionally difficult without relying on these techniques. So let's jump in and let's start with an example looking at a theorem. In this case, you can apply these techniques to theorems, to proofs, or to deductions, no problem. So let's start with an example that you're familiar with. So by now you've proven this maybe one or two different ways using different techniques. By way of illustrating this fairly advanced technique, what I want to do is start with something that you're familiar with. So let's look at this theorem. Now, my first question for you is, let's suppose that you were to prove this as a theorem using CP. What would your assumption be? Okay, so by now you should know right away that your first assumption would be A, and you would be looking for this, if B then A. All right, now what you can do, if you like, is you can nest within that assumption, okay, an IP assumption. So this is a CP assumption, right? We're looking for A, the antecedent. We're assuming A, the antecedent, and we're looking for the consequent. This is a CP assumption. Within that, if you want, you can make an IP assumption. And your IP assumption is going to work the same way all IP assumptions work, which is that you're going to assume the negation of what you're looking for, which in this case is this guy. All right, so we're going to assume the negation of that now, and what we're going to look for now instead is a contradiction, any old contradiction. So let's take a look at how this works in practice. All right, so since we're proving a theorem, we have no premises available, and our strategy here is not to reverse engineer to an axiom. Instead, we're going to make an assumption, and our first assumption that we make is going to be A, right, just as we noted right here. So all of this is working the same as before, all right, no questions asked. And so we're going to write a sump, and what we're looking for now, which is if B, then A, just like this. And so then what we're going to do is we've decided that for this particular example, and there are other ways you can go, we're going to nest within this a IP assumption, okay? So in order to do that, we're going to make another assumption, and it's going to go right here. And what we're going to do is we're going to assume the negation of what we're looking for, which is this, right? And we're going to write a sump looking for what? A contradiction, okay? So this is what we're looking for. So notice what we've got here is we've got two assumptions, but one's a CP assumption and one's an IP assumption. The IP assumption will almost always come after the CP assumption, okay, just like we have here. So now what we're doing is we're trying to use 1 and 2 to build a contradiction, and then we can discharge this particular assumption, and then once we've found this thing, we can discharge this particular assumption. So let's see how it all works together. We're looking for a contradiction. Shouldn't be too tough to find. Fortunately, looking at this, we've got A available. We also have A in here, so we're probably going to find A and not A, but let's go ahead and just use impla, see how it works here. We've got impla on 2, and then it looks like we can De Morgan's that, and this should work out pretty well, right? De Morgan's on 3. Okay, and all I really need is the not A, so I'm not even going to bother double negating. I don't need to get the B out. So that's com on 4. And this is 6, not A, no problem. Okay, so that's simp on 5. And then we can, of course, build the explicit contradiction just by conjoining A and not A together. So we're going to go ahead and do that. And that's conjunction on 1 and 6. And okay, this all works the exact same way as before, okay? So having found what we wanted from this particular assumption, with this assumption, what do? We close it out the exact same way we've been doing before. I'm not changing a thing on you, okay? This all follows the exact same format as before. So we're going to have the thing we assumed, which was this, arrow, the last thing we got, there's a little more space here, which is going to be this thing in this case. So let's go ahead and put that in there. Okay, so this whole thing here implies this contradiction, and that is, of course, IP 2 through 7 in this case. And now, how do we follow up all of our IP assumptions? They work the exact same way every time. Nothing's changing. We're going to follow it up by, pause now. All right, hopefully you have this down. LNC, then modus tollens, and that's going to be modus tollens on what, 8 and 9. Okay, and then it looks like we're going to need a double negation here, so that'll be double negation on 10. Okay, so let's go ahead and fill this in a little bit now, and hopefully you've been able to pause and work this out yourself, but we're going to get, it's not the case that a contradiction holds, right? And that's our handy axiom, the law of non-contradiction, setting up modus tollens, which is not if B then A, right? Okay, so nothing's changing. This is all the exact same structure and format as everything we've been doing. Of course, we can clean that up using double negation. We will here, all right? And now, having obtained what we wanted, look at that, from this assumption, which is as yet not discharged and needs to be discharged, what do we do with this particular assumption? Okay, well, we discharged that assumption. And so what do I write down here? Pause now. Okay, it's going to be the first thing I assumed, arrow, right? The last thing I got, which is this. So maybe it'll all fit in here. That would be nice. Not quite. I'll bring it down so you can see it. But this thing, arrow, the last thing you got, which is this thing, okay? And that's going to be, let's see here, that's going to be CP. That's a conditional proof assumption, right? Because we didn't get a contradiction. CP 1 through 11. All right? And that is QED, okay? So this is a proof, because there's no premises, right, that this is a theorem of logic, and the technique that we used to get this was basically to make a CP assumption and then within that nest an IP assumption, and this is sort of what it looks like schematically once you've done it all out, and everything behaves the exact same way you would expect and in the natural way we've been looking at. Okay, so hopefully the technique here makes some sense. Let's look at some more examples so that you can grow in confidence with it a bit. Alright, so for this example, we're actually going to prove the same theorem. I just want to show you a variation on the proof, and it'll give you a variation on the technique as well. So in the last case, what we did was we made an assumption, right? And that assumption was sort of, we're just going to assume A, and we're going to look for if B then A, right? So all of that was exactly what we did a moment ago. And then we made a second assumption, which was assume the negation of what you're looking for and then find a contradiction. We did that, and it was fine. But there's another thing we could do here, okay? And since what we're looking for now is itself a conditional, as you know, we could instead assume B and look for A. And now within that, we could assume yet again another assumption, right? And this time, not a CP one, but an IP one. And if we're looking for A, and we're going to now make an IP assumption, my question for you is, what would we assume? and what would we look for? Okay, so now what we would be assuming is the negation of what we're looking for, which is this, and then instead we'd be looking for a contradiction, anything of the form P and not P. So let's pull up a chart and see if we can begin filling it in to solve this same theorem this way, where you've got two CP assumptions and you've got an IP assumption nested into the second one. Okay, so since in this case we're proving a theorem, what we need to make sure we do is, know that we have no premises and we're not reducing it to axioms, which we could do, but instead what we're going to do is we're going to invoke our assumptions. So pause now and see if you can fill in all of our assumptions. I'm going to work through them here, but our first assumption would be A, and we would of course be looking for if B then A given that assumption. All right, and so now that we've made that assumption, what we're going to do is we're going to follow our schematic here. And so we're going to nest another CP assumption within that, which in this case is just going to be B. And we're going to mark that as an assumption, and we're going to be looking for A. And now what we're going to do is we're going to make yet a third assumption, but this time it's an IP assumption. So we're going to assume the negation of what we're looking for. We're looking for this. Here's its negation. And we're going to mark that down as an assumption, and we're going to now be looking for a contradiction, and any contradiction will do. So what I want you to do now is pause and see if you can build a contradiction. Okay, this isn't too bad, right? I mean, this one, the contradiction is manifest. And so you see the power of being able to make assumptions and nest them and make IP assumptions, right? It gets you a lot on the board to play with that you otherwise wouldn't have. And so we're exploiting that here. This is conj on 1 and 3. And now, having obtained what I wanted from this particular assumption, what do I do with this assumption? Well, of course, what I do is the same thing we've been doing all along, right? I discharge that assumption. So I'm going to get not A, and then what? And then arrow, A and not A, the last thing I got, which in this case is this, right? So it's going to look just like that, and I'm going to mark that down as IP 3 through 4, okay? So this was a indirect proof, because I found a contradiction, okay? And this is interesting now. How do I follow up all of my IPs? There's a schematic form to this that you have to do every time. What is it? Okay, so you're going to deny that the contradiction is true. Law of non-contradiction, right? So that's going to be our axiom LNC. Then you're going to apply modus tollens, right? Modus tollens on 3 and 4 yields not A. And then, of course, we can clean it up using double negation, just double negate 5 to this. Interesting. And notice, this, of course, is precisely what we were looking for from this assumption, which we have not yet discharged, but which needs to be discharged. So we're going to write here what? Okay, hopefully you've got this, but you're going to get if B, then A. So you're going to get, once again, nothing's changing on you, okay? You get thing you assumed, arrow, the last thing you got, all right? So that's going to be CP 2 through 6, right? Okay, and then, of course, having obtained what we wanted from this assumption, right? It's right here. We can discharge this final as yet undischarged assumption and finish our proof. So what gets written in line 8? Pause now. Okay, well, hopefully you can see it, but it's just our handy theorem that we were trying to prove all along. So it's going to look just like this, right? And that's going to be CP 1 through 7, and that was an alternative way of doing it with 2 CP assumptions and a third IP assumption built in. Let's look at some more examples on the next video. See you on 3.9b.